myself. I started the recording, and I'm just going to first share the screen. Not this one, essentially. I'm on mute over there. I hear myself back. Look at that. Now, okay. Okay, guys, please quiet. Let's get it started. Happy Thursday again. Now, before we start, in the first 25 minutes, I'm just going to walk you through the overall map that we need to do. The overall map that we need to do. Then that's going to be a roadmap for today and next week. By the end of the next week, we are just going to show the pathways for the synthesis of these two molecules. Look at that. The one that you see on the very far left, this is a molecular structures of the morphine. Okay? It's a kind of a modern analgesic. Okay? Now, by the end of next week, we're going to be able to show the pathway. Is it you? Let me see. Hayal? I muted you, no worries. And now, by the end of next week, what we do is that we are able to show the pathways to move from the morphine and synthesize the codeine, the structures that you see on the far right. And also, in between, you see that also we are just going to devise another pathway to build another structures, which is called folcodine, which is another derivatives of the morphine, which is a very good thing when it comes to drugs and medications, which is important for cough suppressors. For example, when you have a cold, if you just get something like, for example, the Buckley, those kind of medications, that it helps you to suppress coughing, it has that thing which is derived from the morphine. This is a big roadmap that we have. And by the things that we're going to learn today and next week, we are able to synthesize these two molecules. And also, if we get some time, I'm going to devise some simulations for you using the AI that we are just going to run it in the class to execute them in the class to see that how you can just work with them in terms of, I should say, reconstructing new molecules that you are not able to do in the lab. And you use that, the AI, to produce these ones. This is going to be our very important roadmap for this week. We are going to be able to do that. However, for this week, by the end of today, we need to have a bridge between what we know right now, which almost, I'm sure you all come from some of you come from the biomedical sciences, some of you come from the pharmacy sciences, pharmaceutical sciences. You know some stuff. We are just going to add to that in order to be able to do so. But in between, we need a kind of a bridging point to do so. And the bridging point is that we are going to be able to add this one very important thing in pharmaceutical sciences, medicinal chemistry, and it's going to be that. Adita is going to tell us what is that. You are falling asleep, brother? Huh? You want to go outside for a coffee, come back? You're fine? Huh? You're fine? Yes. Then what we do is that today we can address that aspect, that how the environment of the reaction, it promotes the reactivity of the groups. Huh? For example, how modulating the acidity or basicity of the environment has a significant impact on how the reaction proceeds. By doing so, we are going to be able to solve this one by the end of the day today as a bridging map. And you see that the thing which I have there is a peptide sequence, a short peptide sequence, But what we're going to learn today is that we are just going to see that how the solution that we are just going to culture this polypeptide, short peptide sequence in that has an impact on the charge and the functional group that this short peptide can form in that environment. When we finish this, we are just going to end the session today. By the next week, we are able to build and synthesize codeine from the morphine. And that's going to be our roadmap. Now, I'm just going to stop the share. Oh, no, I should have just continued with that. I don't know why did I stop the share. I'm just going to go back to this. I'm going to write on this one. Then I'm just going to go back to those slides. Okay, now, the thing that I'm just going to discuss today somehow builds on the things that you have learned from the chemistry one. And we are just going to focus today on the concept of the acidity and basicity. Then from there, we just go to the reactivity of the functional groups, because you're going to see that the concepts of the acidity and basicity is an omnipresent concept in medicinal chemistry, organic chemistry, because it has a huge impact on the reactivity of the reagent and the substrate inside that environment. You remember from chemistry one that you had two definitions of the acid and base. The first definition that you had from chemistry one, which I'm just going to call that definition A, it was called Bronsted-Lowry definition. What was that definition? We just saw that before in the chemistry one. We saw that if we have any structures, like for example, I'm just going to call that HX. HX, it comes with the hydrogen, and X is another element that they are covalently bound in order to stabilize the energy to make the octet. Then you see that the best case, because I have only one bound between them, to stabilize the structures, X comes from group 7 of the periodic table to make it octet, like the fluorine, chlorine, bromine, iodine. And you saw that from the chemistry one, that if you have this inside an aqueous solution, like the water, I'm just going to show the water in its chemical structures over there. The tetrahedral, you see that? And if you have this one in this structure, you saw that from chemistry one, you can expect this thing to happen. Let me take this one, the bottom of the page. I have more access to that. Then you remember you're going to have some reactivity happens because you are just in the polar solvent. First of all, you remember from chemistry one that there is a huge contrast of electronegativity between the hydrogen and the X, which is from the group 7, from the halogen elements. Then as a result, because of the contrast of electronegativity, which it shows that it has a huge hunger for the electrons, which is shared, is gonna take away these electrons from there. And that's what happens. For example, imagine you two just go. Have you gone for camping in Canada so far? Have you gone camping? You see, no? For example, imagine you two go for a camping and it becomes winter and it's cold during the night. You have only one blanket to share, okay? And one blanket to share, it's cold, you're shivering. Which one of you is stronger between you two? Which one is stronger? Which one has a huge muscle is stronger? Casual, for example, you're stronger. What you do is that you remove the blankets in the middle of the cold night from Sonia. That's what happens over there. That what's happened over there. And the hydrogen is like Sonia there. Compared to Kajal, he has less strength. Strength over there is electronegativity. And the blanket is the Lewis bound between them. You take away the blankets, then what happens there? The hydrogen removes without the blanket. Okay? Now, what do you think is going to happen with Sonia over there? Freezing. But she has to come with a solution. She sees that, for example, you do. For example, she says, you two, you are camping also on the next one. You have extra blanket. You give a blanket to Sonia. And what happens? Look at the blanket that you have. Look at that. Look at this one that I have over there. This lone pairs of the electron, which is not part of the hybrid resonance structures, which is not bound to that structures, is like the free blankets that you have folded it in your tent in a camping. We can give it to Sonia. And how it happens if you move it, and in this case, you remember from the last week structures, we said that you show the movements like that with this arrow. This arrow, which I show something like that, it shows the direction and motility of the electrons from somewhere with the reservoirs of the electron clouds to somewhere which is deficient from the electron clouds. Then if it happens, you expect to see this one. You see that. Now, hydrogen. This is Kajal with extra blankets. Now it means that it has 4 lone pairs. You got 1 more electrons more, you get the negative charge. And also, you see that. Now, distance that you have given your blankets to Sonia, you have Sonia coming under your tent because you gave 1 lone pairs to that. Now, then you see that I formed a bond. We are just talking about the broad lower definition of the acidity, but you see that I formed a bond over there. And you remember whenever you form a bond in organic chemistry or general chemistry, you have to stop. Or whenever you dissociate a bond, you have to stop, find the formal charge. How to find the formal charge? We just came also, you remember we have 1 lone pair also, you forgot. 1 lone pair is spent to create the bond. You see the 1 lone pair is created the Lewis band over there. You are left with 1 band over there. And now, in order to find the formal charge, you remember I said that you have to just go to do fishing. What I'm going to do, I'm going to find myself in a position that I see the bound which I formed is between 2 elements, 1 hydrogen, 1 oxygen in that structure. Then I'm just going to position myself in both heads. First, I'm just going to stand on top of the oxygen. I put my hands in my pocket, I draw a fishing net. I'm just gonna draw the fishing net around where I'm standing. You see the dot, 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 dot? Now, I'm asking myself 2 questions. The first question is that I ask myself where I'm standing there. Where am I standing? What is the address? In chemistry, when you are asking for an address, you just go to find the address based on the map of the periodic table. It means that what is the columns of the periodic group that oxygen belongs to? It is group 6, exactly. Then I'm going to write 6. Then the next question and the final question which I'm going to ask myself is that how many fish I have taken in my fishing net. Look at that. I have already 2 electrons. By fish, I mean electrons. Sorry. It's the story, I mean electrons. Exactly. I have 2 electrons already there. You see that these ones are electrons, the cross which I'm making. These are also electrons. How many fish total in the net? How many electrons? 3 plus 2, 5. Then I see I have 5 electrons. I subtract them. I come to this number plus 1. What is the significance of that plus 1? It is the formal charge of the oxygen which I'm standing on. This is very important to be able to find the formal charge, because if you do not find the formal charge correctly, it means that, for example, you are just going to make an apple pie today at home. Who likes apple pie? You want to make an apple pie today at home? You drop beef inside the apple pie. It's awful. Huh? What? Yeah, that's the most important one. Then you saw that the formal charge, which I formed over there, it becomes what? A positive charge on the oxygen. This is so important. You're going to see the importance later. The next thing, you see that also I created a bound on with the hydrogen. Means what? I'm just going to go again, stand on top of the head of the hydrogen, because the bond which I formed is connecting the oxygen with the hydrogen. Then I have to go for fishing for both these elements. I stand on top of the hydrogen. Again, I draw a fishing net. You see, I'm standing here. I draw a fishing net around the hydrogen. I ask myself 2 questions as usual. What is the address of the place which I'm standing? Hydrogen in periodic table group 1, then my address is +1. How many fish or how many electrons is in my net? You see, there is only one. Because your fishing net crosses the Lewis bound in between, then one fish is inside the net, one is outside of the net. Then I have one electron, I subtract them, I get 0, which means that the hydrogen has a 0 formal charge. There is no charge change for that. Then I see that the only formal charge which I have for this structure is what is essentially on the oxygen, which you remember from uh, chemistry 1, we call this structure H3O, we call that hydronium. Now, these structures that we show, this example that we show, it was a review of the things that we did in chemistry 1 when we discussed about acidity from the perspective of the Bronsted-Lowry acid. Then in that case, you saw that you have a hydrogen ion which becomes mobile. It moves from one element and it's taken by the other compound. The compound that releases a hydrogen element, hydrogen ion, we call that what? Bronsted acid. The compound, for example, HX, it becomes acid. On the other hand, the other structure, which is water over here, which was a recipient of the hydrogen ion, you cannot look at that. It's like what? The hydrogen ion is like, have you seen $100 bills? Yes. Do you expect that if you go outside, you go to the Midland Avenue, you put your hands in your pocket, you take out a $100 bill, you drive to the street, do you think that that $100 remains on the ground intact? No, somebody jumps to take it. That hydrogen ion is like that $100 bill. You have a hydrogen ion in the solution, it's going to remain there without being taken up. Somebody comes to take this up. And the structures that you had over there to take this hydrogen ion, which is water, yeah, we call that base, Bronsted base. Now, I just go to the right-hand side as a review. These are all the review for chemistry 1. I go to the right-hand side because I reached an equilibrium. If I go to the right-hand side, I see that if I look at the right-hand side, I see, for example, the X, which represents probably chloride because the X is from group 7. I see this one has a negative charge. In presence of the hydronium ion, everything becomes reversed. Now, the hydronium is very energetically unstable because it has a positive charge on the oxygen. You're going to see that in the coming weeks, that the oxygen cannot have a positive charge on it. Because oxygen, when it comes to the positive charge, it shows electron deficiency for the oxygen. And it's not acceptable because the electron is very electronegative and it cannot be electron deficient. Then as a result, it's going to kick out. It's going to kick out the hydrogen, and the hydrogen is going to be taken by the X ion. Then the thing becomes reversed. Then the X ion is accepting now that hydrogen. And then in that case, we call that, it becomes base, but we call that a conjugate base. But now hydronium ion, that now is releasing the hydrogen, conjugate, it becomes conjugate acid. Because now if you look at it from the reverse perspective, now the things becomes different. Now, all the things that we discussed was a kind of a review for the things that we discussed I didn't discuss that with you, but we had it in chemistry 1. I'm going to introduce one topic, then we take a couple of minutes quick break, because the next one is going to be a little more mathematically involved. I need you to be more focused. For this scenario that we discussed about the Bronsted acid and Bronsted bases, I'm just going to come to discuss about a concept that you had in chemistry one. In chemistry one, we discussed about equilibrium. In the equilibrium discussion that we had, what time is it now? You are still decent, huh? In, in chemistry one, we talked about the equilibrium. I need the concepts in order to, this concept becomes a dominant concept. I need that to remind you of that. You remember in chemistry one, we said that if we have two reagents, A and B, they come into react inside the solvent, which they create, for example, the products G and H. Now, we needed to make sure that the conservation of mass is valid. Then as a result, in chemistry one, we introduced the concepts of the stoichiometric coefficient just for the purpose to conserve the mass. Then as a result, I'm just going to write those coefficients with the small letters A, B, G, and H. Now, in chemistry one, you remember, we came to discuss an equilibrium constant. We said that, okay, we find an equilibrium constant, which is going to be the kinetics of the backward reaction with respect to the kinetics of the forward reaction. Then I came to introduce this one, equilibrium constant. I call that K, which stands for something which we normally symbolically use for a constant. Put EQ on top of it, which stands for equilibrium. And I say this constant is equal to, which is a temperature dependent constant, which is equal to the products of the products, is the concentration of, for example, H. It is not hydrogen. It's a symbol for one of the products to the power of H times G to the power of G, stoichiometric coefficient, divided by the products of the reactants, A to the power A, and B, concentration of B to the power B. That was the thing that we talked about in chemistry one, about the equilibrium constant. We saw that we talked about the dependence of these ones on the temperature. And also we talked about the Le Chatelier principle, that how you can just retransition this constant by changing either the concentration, the temperature, the pressure, or anything. I'm not going to go into those kind of stuff. I'm just going to say this one in terms of to remind you of one concept that we need to know for the purpose of acidity and basicity that we discussed today. Now, I'm going to come with the same scenario that we had. Instead of HX as a symbolic representation for strong acids, I'm just going to call that HCl, hydrochloric acid, which you remember normally comes in a gaseous state. You dissolve it into water, which I call it L, means liquid. G means gas, L liquid. You remember from chemistry one, when you introduce the bubbles of the hydrochloric acid inside the beaker, which has the water in a very specific temperature, you are forming what? Hydronium ions, which you remember from previous slide, which is aqueous solution over plus Cl, still in aqueous solution. Nice. That's what you remember from chemistry one. However, we see that after a while, if you do not change the temperature, you keep everything constant, the conditions of the reaction, you see that it comes to an equilibrium. It means that the rate that the hydrogen is going to be dissociated from the chloride matches the rate that the hydrogen is going to form back to the chloride, comes back to this state. Then now, Although the equilibrium, I have to say, the equilibrium is formed in that condition. I have to be careful with that because you see that when I show the equilibrium, I have two arrows. The arrow which it goes to the right, which it forms the hydronium formation, is much longer than the arrows which shows the formation of the hydrochloric gas. Because although we reach the equilibrium, the formation of the hydrogen is much faster and more dominant. Now, in that case, I'm going to come to introduce a constant. A constant, which is the equilibrium constant for this acidic reaction, comes based on the definition that we had. The concentration of the hydronium, the concentration of the chlorine, all the stoichiometric coefficients are 1, then everything raises to the power 1, divided by the concentration of HCl. I omit the conversion of that in the gaseous format to the aqueous solution. Then now as a result, I do not also introduce the water because we assume the activity of the water is 1. I'm not going to go in there. You just had it in chemistry 1. In that case, the equilibrium constant for us here is just for this acid reaction. That's why I call that Ka instead of K equilibrium. Now, we reach to 2 points. The most important thing is that I'm just going to finish it with this very important conclusion that we needed when we come back from the break. The first thing is this. Then you see that if the hydronium concentrations becomes too much, if you have in a solution higher concentration of hydronium ions, for example, imagine that inside the class, every girl represents the hydronium ion. Every boy represents the chloride ion. What hydronium ion represents is the acidity. Then you can expect that the more girls that we have in this class, you feel more acidity in this class. It's just for sake of example. Don't think that I said the girls are have acidity. This is kind of an example. Huh? Now you see that then the more hydronium you have in this class, imagine the more girls you have in this class, you can feel more impact of the girls in this class. They become more dominant. If hydronium ion concentrations goes up, you see that this proportion Ka goes up. Okay, this hydronium ion concentration goes up, Ka goes up. And this is one important conclusion. The more hydronium ion represents a bigger Ka value, implies strong acidity. This is important when we come back from the break. Sometimes we say, for some acids, you see that they are weak acids, then the number of the Ka becomes very negligible. Then we can mathematically find a solution for it. We say that sometimes we work with very small numbers. Then I devise this one. I say, I look at the Ka which I have. I'm going to take the logarithm of this. And I'm just going to put the minus sign next to that. You see, I'm just playing. There is no rational behind that. I'm just going to squeeze the numbers. That's why I do that. Because I just want to squeeze them, I introduce the log because some of the very weak acids, they have 10 to the power minus something, very weak number. I introduce the minus sign there. That's the mere rational behind it. Then if I create this ratio minus log at the base 10 of the acidity constant, I'm just going to call this one pKa. And it becomes the most important thing that you need to know for the rest of the organic chemistry class. Because in any solution that you're going to work with it, you have to know the pKa value of that. pKa value, it implies what? Then you see that if you have a very strong acid, you expect to have very strong, let's say, Ka value. Because a strong acid, look at that. Everyone listen to this, it's very important. I finish it with this one. Then after the break, we just have some problems to solve. Remember, a strong acid comes with a strong elevated concentration of hydronium ions. The elevated of hydronium ions give a bigger Ka value. But because you took a minus log of that, it gives you a smaller value, which becomes very important. Then for the last time, strong acids comes with big Ka value, but with very small pKa value. This is very important. But we look at these things in context of the relativity. We always compare pKa value of the functional groups that we learned last week to the pKa value or the pH of the environment. Then that comparisons tells you a lot in order how to initiate the reaction. Then what we reviewed right now becomes a most important thing in organic chemistry and medicinal chemistry to see that what kind of an appropriate environment you need to in order to change the direction of the reaction. Now, speaking of which, it gives us to a very interesting moment right now, and that is the sweet break. Any question? Are you sure? Yeah? Okay, I'm just gonna.
Innovation.
Haru,
ठीक है ना
bless you.
एक तो
Guys, please quiet. I just started the recording.
okay okay wait
What do I need to do now? Okay, now I'm just gonna share the screen from almost what we did before we just went for the break. However, remember that at this stage, let me share the screen. Okay, now I need to, for this time, before the next break starts, how's everyone doing? Good? I'm just checking to see it's okay. Yeah, yeah. Until the next break that we're just gonna do, I'm just gonna practice the things that we did for the first part of the class. With respect to the acidity and basicity, I'm not talking about yet the Lewis basis. Lewis basis is gonna be the next one because you see that we're gonna talk about nucleophilicity, and that becomes what did you? Let me see. Now, then you are going to see that the thing that we are just going to do next week, I think everyone is mute. That's good then. Then now, but the thing which I'm going to do right now is to practice what we learned about the acidity strength captured either with the Ka or pKa value and see the significance of it into the reaction. Because remember, sometimes the functional groups, you remember the last week we talked about the functional group, for example, carboxylic acid group, alcohol groups, or for example, amide groups, those functional groups. We said that the significance of these groups, they are the things that orchestrate the reactivity. If, for example, you're going to see by next week, when we are just going to start working on the morphine to see how you can build codeine, you see that the whole structures of the elements that you have. Let me just go back to that thing that we're just going to see. For example, look at here. Let me use this. Look at this. You see the morphine on the left. You see that the whole structures that you have there, the reactivity comes from two parts, and the rest of the structure may have not any direct implications from where you start from the morphine, which is from the left, all the way go to the right, which is codeine. You see, there are two functional groups. One of them, you see, it's going to be this structure, which you remember from the previous week, from the chart that I gave you. This is called phenol. You have a benzene ring, aromatic structure, hydroxyl group attached to that, which is phenol. This is one functional group. And the other functional group is going to be this hydroxyl group. And you're going to see that next week. Almost the rest of the structures, it seems as if they do not exist in the reactivity directly. And all the things that we're going to do next week, you see that these two things that I highlighted them, it's going to orchestrate the pathways all the way that you build codeine. And that's why important. You need to understand the functional groups, because if you do not know the functional groups, how can you know that where you have to start? That's the first key thing. And the second key thing is that these functional groups that you see over there, it seems that they are dormant. They are sleeping right now. They're taking a nap. You have to wake them up in order to say, okay, imagine that this is going to be the soldier who is going to go for a fight. But before you send him for the fight, you have to wake him up. You say, oh, hello, wake up. There is a fight. You have to go for it. In order to wake them up, we need the environment with a relative acidity or basicity. You're going to see what do I mean. Then the things that we discussed today and the example that I'm just going to discuss it right now with these structures that we have, which is the short peptides, it prepares you for the synthesis of the codeine. Now, I'm just going to do one example to see what do I mean that you have to wake up these functional groups. If you want them to send them to the war, by the war, I mean the synthesis pathways. Now, the thing that you see over there in this slide, this is the thing that you saw that in biology 1. What is that over there? Amino acid. You remember the amino acids, that's right, they are the building units, the building blocks of the proteins. You connect them together to make a polypeptide. Then you just configure them based on the hydrophobicity that they have to fold them to make a functional proteins. That's what you saw in chemistry in biology 1. Now, with this one, with this amino acid, which you see on the right side, for example, you have cysteine, you have phenylalanine, you have valine. There are amino acids there, but you don't need to know these structures. I just put them in order to demonstrate how do they look in terms of the molecular structures. But in the left side, you see that for the amino acids, I have very, very central element, which is a carbon, which is important. We call it alpha carbon. You see that we have always a hydrogen there on the top. There are two functional groups, one on the left, one on the right. On the right is amino group, NH2. You see that because nitrogen comes with 5 electrons in its valence bound, you expect to have a lone pair of electron there. And you have on the right side carboxylic acid, which is another functional group, a very important one. You're going to see that by this example that we do. We look at these functional groups as the terminals that they manifest acidity or basicity. What does it mean? It means that they can show that they can either accept or they can release hydrogen because they're just going to come under the category of acidity basicity. Now, if that's the case, if they are representing the property of being either acid or base, then we have to come to attach them to the pKa value. Remember what we discussed before the break. We said that you can assign to any compound this value, which is pKa, which shows the relative strength of the acidity. I have pKa for the ammonia, which it shows that the acidity. I'm just going to give it based on the experience, something around 12. And for the pKa of the carboxylic group, you can measure them by the amino acid titration. You can give them a pKa value of approximately 6. almost half of the amino terminus. What does it mean? Means that the amino terminus and carboxylic acid terminus, they can accept or release hydrogen. They have acidity. Which one is a stronger acid compared to the other one? Is the one which has a lower pKa value. Remember previous session? We said that the lower the pKa value, the stronger acidity. We saw that based between the acidity and the pKa value, there is an inverse relationship. The bigger the pKa value, the weaker the acid. The smaller the pKa value, the stronger the acid. Then you see that in that case, the carboxylic acid, as the name also implies, has a stronger acidity compared to the other one. Huh? And that becomes very important. Now, then as a result, I'm just going to mention something very important. Now, if you put them inside, let's say, a solution like, let's say, ammonia, or in a solution that it has its own pH. Imagine that you put these amino acids inside the cytoplasm or interstitial, I should say, fluid of the cell, which has a physiological pH of how much? 7 point around 6. Huh? If you have a pH of around 7.6, and you remember also from chemistry 1, the pH is minus log of the hydronium concentration. You remember from chemistry 1. Now, look what happens, because I'm going to use this one in order to find the charge on a sequence of amino acids, which is going to be the peptides. Now, look at this. Now, I have in this structure the pH of the physiological condition is 7.6. I have carboxylic acid, a pH of 6. Now, the important thing is this, that also you have to take care of that for the midterm, is that when you're looking for these structures, you do have to look for the relative pKa value. A single pKa value and its entirety, it doesn't signify anything. But if you compare them, you can understand what's going to happen. I'm looking at pH 7.6, pKa value of the carboxylic acid. I see that the pKa value of carboxylic acid is less than 7.6. It means what? The pKa value, which is smaller, it means that this is more acidic. Huh? Then as a result, if it becomes more acidic, what happens? It's going to donate a hydrogen. It is very important. Let me erase this because I need that space. Look at that. I have the carbon here. I have carboxylic acid here, the carbonyl group here, the oxygen and the hydrogen. And I have, this one has to be carbon. This is R. R is a side chain. It can be anything. Nitrogen, hydrogen, hydrogen. And look what happens. And a lone pair over here. Now, the pH is 7.6. Let me take this one, bring it over there. Now I change the color. And now, the very interesting part starts right now. We see that the pH is 7.6. The pKa value of these terminus is around 6, which it means that it is more acidic than the environment. If that's the case, it means that it acts as an acid. What is the role of an acid? If you see the chemistry as a theater stage, an acid has a role. The role on the stage is that to give out the hydrogen. But what hydrogen is going to be released? The hydrogen which is from this hydroxyl group. Then as a result, you see that this hydrogen is gonna be pushed away in the solution The polarity also helps it because it's more or less, it's a polarized band. That hydrogen is going to leave. Then as a result, you see that the carboxylic acid which I had becomes ionized. Let me, let me, I wish if I can remove that picture. No, I cannot. No. And this hydrogen is going to go out. The hydrogen goes to the environment. The hydrogen here goes to the environment, which is positively charged in the solution. However, now I come back, and also there is a hydrogen which is bound to that. I forgot to mention that. However, there is another thing which happens, is that the hydrogen there in the solution, now it has a positive charge on it. It may forms a bond with the solvent structures, but imagine we look at the case independent of the solvent molecular structure, and we assume that the hydrogen ion is wandering around. And look at the other terminus. The other terminus that we have over there is amino group. The pKa value is how much? 12. But the pH is of the environment 7.6. Means that now the environment is more acidic to the amino terminus. If that's the case, in the tertiary stage of this reaction, what is the role of the environment right now? Becomes more acidic because the pKa value is smaller compared to amino group. Then as a result, if the role is acidic, he is going to kick out the hydrogen outside. If it's that the case, is going to be the hydrogen is going to be accepted by the amino because bases accept the hydrogen, and you see that the electrons, hydrogen is going to be taken up by the nitrogen, which has a lone pair. The lone pair is going to form the bond. I'm going to write it on top. I'm going to write the structures down on top. Then you see that everything happens. What do you end up with? You have the central carbon there. You have the carbon of the carboxylic acid there. The oxygen remains there. There is another oxygen, but now it comes, look at that. Here we have 2 lone pairs. Now we have 3 lone pairs. You find the formal charge. As I said, you find a negative charge. The hydrogen remains there. The side chain can be anything, remains there. The nitrogen initially at 2 hydrogen. 1 hydrogen has been taken up from the environment because it had a higher pKa value, gets 1 more hydrogen, but it becomes positively charged. You can test it. You can do the formal charge. For the nitrogen, you see that it becomes positively charged. You ask yourself, what is the address of the nitrogen? It is 5 on the periodic group. You have 4 electrons around it. 5 minus 4 becomes plus 1. That's why it becomes positive charge. But now you have an element, you have an amino acid that has 2 charges at the same time. 1 positive from the amino terminal, 1 negative from the carboxylous terminus. That we call that Zwitter ion from biology 1, if you remember, which we do not care. But the significance of this example here was that, woke you up. The significance of this was that you saw that a single amino acid in the environment got a different configuration in terms of, I should say, the ions which it adopted. You woke up the functional groups, the terminal carboxylic acid and the amino terminus, they got woke up by the movements of the hydrogen. Why that happened? Because you had an environment with a pH which is different than the pKa value. Then the final point is this. Then any time that we are just going to work for our case, for our solutions, for whatever we do for all the way to week 15, it is important to know the pKa value of the functional groups and the pH or the pKa of the environment. By comparisons, then you are going to wake up the functional groups in order to orchestrate the reaction for you. Sounds good? Any questions? No? Everyone's happy? I'm gonna do the recording. I'm gonna share the screen. Not this one. Not this one. You guys, please quiet. Nah. Okay. Now, look at this one. First of all, this is gonna be the last session for today. There is no more break. When it's finished in 20 minutes, what do we do? Oh, yes. We do that, then what do we do after? We go home. Now, the thing is that the next thing that we are going to do before we just go back to the synthesis of codeine from the morphine, which needs more content to learn, I'm just going to do a practice because what we did learn before was that the importance of the pH or the pKa value of the environment with respect to waking up the functional groups of a compound, that it implies that it orchestrates the rest of the reaction. We saw that before. Now, I'm going to create a very short peptide. A short peptide, that means I'm just going to take 4 amino acids, linking them together. I just start from the amino terminal, extended by the end of the carboxylic acid terminal, by the 4 amino acids, drop it inside the solution, which has a characteristic pH. Then I see that what happens to the functional groups when you consider relativistically the pKa of these functional groups with the pH of the environment. Then when we learn this one, next week when we start, you see that you're just going to have to start with the basic solution to when you just work with the morphines to wake up the function. Sandeep, I'm so glad you have a question. Ah. Okay, yeah, ask a question, please. Brother, ask a question. No question. Testing how the functionality works, huh? Awesome. Now you see that I have 4 amino acids. I'm looking at them in isolation. Then when I connect them together, we have a more sense that how the peptide acts in that pH that we have. Look at that. The first one that I have, I'm going to put that into the Google Classroom. I'm just going to look at the reference sheet, which I have for amino acids. Look at the glutamate, which it comes with the E abbreviation, which is going to be an acidic one. Look at that. The glutamate. This is the negatively charged. Look at this. The glutamate. This is on the very top. For the midterm or those kind of stuff, I'm just going to give you this sheet. You're just going to work it through to find the amino acids, but I'm just going to tell you which one is which. I'm just going to give you the abbreviation for that. You don't need to memorize it because we do not do the biochemistry, we do the organic chemistry. It's good to know these 3-letter codes or one single code for that, but you do not need to. I'm just going to provide that to you. The first one, which I'm just going to work with that, is glutamic acid or glutamate. You see that. Now, on there, you see we have the central carbon there. We have NH2, which is the amino group that we saw. We have carboxylic acid at the bottom. We saw that these 2 terminals, they have the pKa value 12 for the amino, 6 for the carboxylic acid terminal. But you see that the side chain, which is extends up. You see that there? The side chain comes with the pKa value of 4.2. Huh? Sonia? You want to go for a coffee? How about the hot chocolate? You look a little sleepy. Now, then I go back to this one. You saw that the terminus which I had there in that structure, this is glutamate or glutamic acid. This one is a carboxylic acid terminal, which is inherent functional groups with the pK of 6. This is amino terminal, the pK of 12. However, you saw that in that chart. You see that that's what you do for the midterm. You just go to see that if the terminal of the side chain has a pKa value of its own. You just saw that on the cheat sheet of the reference paper that you had. You saw that this one, which is another carboxylic acid terminal, it has been measured before. The pKa value of this side is how much? 4.2. This is this one. Huh? This is this one. Now, I look at this one. I'm just gonna look at the other structure which I have. This is another amino acids. We have 21 amino acids. We have only 4 out of them. Now, the next one is a very popular one, which is tyrosine. And I'm just gonna write that tyrosine. You showed it by Y in that chart. You see that here. This is the carboxylic acid terminal of the amino acids. This is the amino terminal of the amino acids. They are just always fixed in the amino acids. They are central to the carbon. They're just connected to the central carbon. What do I have here? You see that there is a functional group there, which is this phenyl group. Benzene ring with the hydroxyl group attached to that. Then now the thing that we just want to ask ourselves is that if this one comes with the pKa value, which represents its acidity. Look at the tyrosine one. The tyrosine one, they are just going to be at the hydrophobic section there, at the bottom. You see these one at the bottom on the right side. You see these aromatic rings. You see the rings. If you see for the tyrosine, tyrosine is the middle one. The tyrosine middle one with the Y abbreviation. You see the pKa value on top of it. You see the phenyl ring with the number on top of it. It's the pKa value. How much is that? 10.1. I got this chart from the Wikipedia. It's very easy to find it. Then you see that for this one, the pKa value 10.1. Now, I just go to the next one. The next amino acids which I have there, still there is no connection between them. I haven't yet formed the polypeptides bound between them. I have them in isolation. The next one, as you see, I have this carboxylic acid terminal. I have this amino terminal, but you see that over here, then we choose this color. You see that this terminal, which is just a benzene ring. This one is phenylalanine. You do not need to memorize these names for the organic chemistry, but I'm just going to give you the chart, which shows it by F. I'm just going to go to that chart, and I see that if I go to the chart, which I have there, what is the pK value of the phenylalanine? Again, at the aromatic ones, which is at the bottom right, you see the chart with 3 amino acids. They have the characteristic ring structures. Vanilla in the first one from the left. You see, I have the amino terminal, carboxylic terminal, but this benzene ring doesn't come with the number on that. It means that it doesn't have any pKa value, which it means that there is no hydrogen mobile from that structure, no acidity or basicity. Then I'm just going to skip it. Then there is no pKa value. Is not defined for it. The next one. The next one is aspartic acid, which you can say that also aspartate, both aspartate or aspartic acid. You show that with D. I'm just going to go there. Look at that. I have my functional groups here. Look at that. I have this carboxylic acid terminal. I have this amino acid terminal. And the side chain of it, the side chain of it comes with this terminal, which is carboxylic acid itself. I'm just going to, this chart which I have there, I'm going then to find aspartate. Aspartate is going to be with the negatively charged. I'm just going to go here. Look at that aspartic acid. On the top, the second box on the right, you see aspartic acid, which it shows that by the D letter. You do not, as I said, you do not need to memorize them. In the exam, I'm just going to tell you which letter they belong to. You see that it's D. You see, with the side chain, which it has a carboxylic acid attached to that, the pKa value is how much? 3.7. Then I'm just going to go there. I said that the pKa value, 3.7. Now, what do I have right now here? Now, now what I did, I identified the pKa value of all the side chains. However, I know that beforehand, the pKa value of the terminal groups, amino group, pKa value is 12, carboxylic acid group, pKa is around 6. This is always accepted. Now, but the side chains, they had a different terminal pKa values. Now, I'm just gonna connect them together. Okay, connect them together and put that in. Let me just work with one of them, then collectively look into them. Imagine that I have each amino acids within a solution. With the solution itself is a little bit more acidic. I'm just going to say that the pH value of the solution is around 6. You're going to see that next week when you're making codeine from the morphine, it's going to be the opposite one. That's the thing you decide what to do. If I put the pH 6, let's see what happens. First, I'm going to look at the glutamic acid. At the glutamic acid, when I see, look, I'm going to compare 6, the pH of the solution, with 3 different pKa values. Because you remember, I said that the pKa values, in absolute terms, they have no significance. You have to always look at them and compare them with the another pKa values. Now, I have 3 comparisons to make. For 2 terminals, 1 side chain. The pH is 6. Carboxylic acid group pH is how much? 6. Then I expect that nothing happens. There's going to be an equilibrium between them. For the amino terminal, the pKa value is how much? 12. This is 6. Means that the environment is more acidic. Remember, the bigger the pKa is less acidity. Then as a result, I see that this is going to be what? It's going to be acidic. Then it gets protonated. It gets a protein from the solution to become NH3. About the side chain, the pK is 4.2. The environment is how much? 6. It means which one is more acidic? The side chain. The less the pKa value, the lower the pKa value, the more acidic they become. Then the more willing they become to donate the hydrogen. Then as a result, you see that the carboxylic acid that you have over there, it releases the hydrogen. The hydrogen goes to the environment, and from the environment, it goes back to protonate the amino group, which we have there. It is one simple example of this. You can do the same thing for all of it, but now I'm just going to go to the next slide, connect all these things together. Collect all these things together. Now, you see that now? In this now, I have formed that very short peptide comprised of 4 amino acids that I had over there. I had glutamic acid, tyrosine, phenylalanine, and aspartate. I made a diester bound between them, okay, a covalent bound between them. Now you see that short peptide. Now the thing which I want to see that is that what is the overall electric charge on this short peptide inside the solution, which has a pH of what? 6. Huh? That's what we are going to do. Now, the first one is now, okay. For the first one, look at that. The first one from the left, it was what? Glutamate. That question, back. Everyone's happy, happy, happy. Are you sure? Are you sure you're happy? Why you're happy? Because you learn good or because you're close to the going home? Which one makes you happy? Now, the thing which I'm going to do is that I'm just going to look one by one. You see that? The first one is a glutamate with the side chain 4.2. Look at this. My side chain is here. Do not worry if you do not see that very clearly. This becomes a little bit bizarre. You're just going to do more practice. You're just going to work well with the polypeptides. Now, the side chain with the pKa value of 4.2 is here. Huh? This is the carboxylic acid which I had. And this is the amino terminal which I had, which they connected to the amino of the adjacent amino acids. However, we don't need to go into much details. What I see here is that the amino terminal with the pKa value of 12, bigger than the pH of 6, it is less acidic. Environment has a lower pKa value, pH, then it becomes acidic. It protonates this one. But at the same time, remember, the pKa value of the side chain is even less than the solution, which it means that the amino terminal and the side chain, both of them are more acidic. Then as a result, this one, which is less 4.2, which is less than 6, it becomes more acidic, releases the hydrogen, but the pK of 12 of this one is bigger than 6, it becomes more basic. Then the hydrogen is going to be taken by this one. Then NH2 becomes NH3. This is for the first one. Then you see that for the first amino acids, the comparisons of the pKa value with the pH of the environment is crucial. Otherwise, if you cannot compare them, you do not see how the reaction may proceed, which functional groups may wake up. Because always remember, in order to wake up a functional group, you have to always make a comparison. Which one is more acidic? And it always happens with a comparison with the pKa value and the pH of the solution. I go to the next one. The next one, you remember, what did we have? We had the tyrosine with the pK of the side chain of 10.1. I just go to the tyrosine. You see the side chain? It is the 10.1 pKa. Okay? This is in between. This tyrosine stands in between. Look at that. You remember from biology 1. When you make a short peptide, the amino acids, they hold their hands together. One hand is amino terminal, the other hand is carboxylic acid. They hold each other hands. The amino takes the hand of the adjacent amino acids from the carboxylic acid group, and that one continues like the line. Then when you see a amino acids in between of the polypeptide chain, not at the terminals, you do not worry about the side terminals because they are being taken by the other amino acids' hands. Then the only thing that you have to concern is the side chains that they have. For the tyrosine, the side chain is 10.1. Now, we are just going to ask ourselves, which one is more acidic? Tyrosine in the peptide or the environment? You say the environment, because 6 is less than the pKa value of the tyrosine side chain, which is 10. Huh? That's right. Then as a result, this one becomes more acidic. The environment is more acidic because it's less than the pK value of this. Then if the environment is more acidic, it's going to push the hydrogen back there at the hydroxyl. The hydroxyl remains there because you cannot add more hydrogen. The hydroxyl remains there. If it was more basic, as you're going to see next week, if the hydroxide, because in its basic environment, the H is going to leave the hydroxyl group of the tyrosine, but it remains there. Now, I go to the next amino acid. You see, this one is what? Phenylalanine. We saw that the pKa value is not defined for that. Then there is no either protonation or deprotonation. Because there is no pKa value defined for that, then there is no comparisons to be made. Then we cannot decide which one is more acidic or basic. Now, I just go to the end, which is going to be aspartic. With aspartic acid, it was around 3.7. Now, with this one, you see the aspartic acid. This is the side chain, 3.7. And this is also the carboxylic acid of the terminal, which had around pKa of around 6. Around 6. Huh? 6 point something like that. Now, this happens what? Now, because you're at the terminal, you see that the amino acids, which is at the front row, the terminal from the carboxylic acid group is empty. Then it's prone to be either protonated or deprotonated, depending on the pH of the solution, and also the terminal. We look at first the side chain. The pKa of 3.7. pH of the environment is 6. Which one is lower? 3.7. Then the side chain of the aspartic acid is more acidic than the environment. But if this is more acidic, the acid, the role that they have in the theater is that they shoot out the hydrogen. Then the hydrogen, which one belongs to this carboxyl, to this hydroxyl group, is going to be leaving. It goes. Then you have a minus charge. Also, look at this one. For the carboxylic terminal also had the pK of 6. The pK of 6, and we assume that the pK of 6 is a little bigger than the, let's say, it's smaller than the environment, because we roughly approximated to 6. It was a smaller, and we assume that this also becomes more acidic, because let's say 5.9 is smaller than 6, becomes more acidic. It also gets deprotonated, and the hydrogen is going to be gone. Now, then you see that what we did so far, we are going to do more practice on that. But what we saw here, the only takeaway, which I expect that you take from this exercise that we had, to understand the significance of the pH of the solution and the pKa value of the functional group in a compound. Because by way of comparisons, you are just going to decide how the reaction may start. Because always remember, this comparison eventually is going to wake up the functional group that it needs to wake up to orchestrate the reaction. And that was one example we did. Don't get yourself to become so much strangled with that, to say, oh, I didn't understand this, I didn't understand that one. The only takeaway that you need to take is that to understand the significance of this one. Good one. Good one. Now, the final point. Now, you see, the peptide that we have now get some charges on that. Let's see how much charge do we have. Now, look at this. Guys, let's see the effective charge. Let's see the effective charge on this short peptide. Now, I have one negative charge here. I have one negative charge from this aspartic amino acid. I have one negative charge here. How many negative charge do I have? 3. And I have a positive charge here, amino terminal. What is the effective charge? -2. Then you see that. And everyone, please listen. You see that. Now, it is a very important conclusion for today. You see that by way of comparisons and by way of building the pH based on our interests and the pKa value there, I created a peptide, short peptide, which is not neutral, which is charged -2, which has a huge implication for its interactions with, let's say, water, to be hydrophobic or hydrophilic, which is a very important consideration that if you design a drug, for example, which it has that peptide, is capable of crossing the cell membrane or not. For example, if this short peptide is conjugated with the drug, this cannot cross the cell membrane because this is charged. And the cell membrane is all hydrophobic. It's lipophilic. It doesn't let the cross and the passage of the charged elements. Then you see that it becomes a very important question to decide that if what you designed is neutral or charged. Because if you build your drug based on that short peptide as a part of it and it becomes charged, you just want to send it inside the cell, for example, to impact the gene transcription as a drug, but it's not able to access the DNA and gene because as soon as it arrives at the cell membrane, it's going to get stuck because it's charged, it's hydrophilic, and the membrane is lipophilic. It cannot cross the membrane. Then that becomes a problem. And now, I hope that everyone do not get yourself so much entangled with, oh, what happens if I had many more amino acids? How did I do that? How you did that? I'm a little bit weak on that. Do not worry. The only purpose for today was that to find the importance of what we did. And that's it, nothing more. Huh? Any question? Let me stop the share. Oh, I didn't have the camera on.